Hey, how's it going, guys? So here we are back at the Python BACnet Stacks playground. I'm just going to run through some commands on making some updates on AWS IoT Core through the Cloud Shell. Um, yeah, so we have kind of a cool little dashboard. So just to get looking at the schematic again. So I'm right here. I am remoted into a little server on my test bench. I've panned the camera before, I think, in other videos, with the Cursor AI IDE from my Windows computer that I'm doing this YouTube video on. And I do have a couple fake BACnet devices or fake HVAC devices running BACnet applications on my test bench. And then also the Boss Pi has this hardwired GPIO one-wire digital temperature sensor. I have a breadboard with some resistors cobbled together, and I'm getting like a sensor reading, and then that is going to the AWS IoT Core, and we're running Lambda functions on AWS, which is pretty cool. This is I'm kind of impressed by this. So the JSON payloads are looking kind of like this. We're calculating in Python in the BACnet application degrees Fahrenheit and degrees Celsius of the temperature sensor readings. Every 10 seconds, we're doing MQTTS to AWS IoT Core. And yeah, it's pretty neat. So let's, on this episode, let's do some fault detection equations in Python. So this might be a lengthy one. So hoping I can kind of muster through a little bit of the computer science theory, and then also got this even running in the AWS Lambda. So I do have some updates. I do have permission to do this in a live HVAC system. So I'm hoping to demo this very soon, where I'll be using Ansible to deploy the Python code on a remote embedded Linux device. So Ansible can update my Boss Pi locally on my test bench, and then I'll have this right here. This will be the remote BAS, where I'll be using Tailscale VPN to go from this Linux box running Ansible through the internet, and then it's not that far away from me, to another building running another Linux instance, where that then we'll be using MQTT to push data across the internet to AWS IoT Core. So I'll be using like a VPN just to upload updates to the Python code running here, and then this device will be connected to the internet, outbound internet, to do MQTT secure without a VPN to AWS, and then we'll be able to run Lambda functions across it. Okay, so enough about this. Just getting back on Python stacks on GitHub. So we're in Vibecode app 12. There's some cool things coming with BACnet routing, some lessons, and then I also have one I want to do, maybe even getting into a couple of these, is doing embedded applications in C. So it gets really hard. So Python is easy, writing C is really hard, and it's on bare metal applications, so no operating system. So it's just a board. So pretty much like when I used to set up HVAC controls, I think most of the applications I was deploying and building automation were just bare metal applications. No embedded Linux, no Raspberry Pi, no Windows, no Ubuntu, just embedded C running right on a chip. So I want to play around with that. There's some BACnet stacks for that written in C that are really hard. So maybe we can even vibe code that. I'm not really sure. So we'll be exploring that. And then also for anyone interested in so I'm going to try and breeze through some computer science fundamentals But if you're just starting out, reference really old videos for installing Python, doing some really basic Python challenges. These are just daily mini lessons created with AI. AI created all these little daily mini challenges. So, and then I'm already down here. I think I went up to here on YouTube, and then I'm kind of jumping right into day 35 stuff, where doing Boolean fault detection logic, just plain vanilla Python, no math libraries, no pandas, no NumPy, or anything like that. I have some ideas for jumping way ahead into if you get just like backing up a step, there is guideline 36 exercises for how to do algorithms in guideline 36, where based off of Java implementations in the Niagara framework, someday, like, we're going to jump all the way into RDF theory. So this is a more, I think, like master's degree computer science level advanced data structures. So, which can be a very broad topic, but I think like we only need to study just a little bit for smart building use, to do data models in brick, haystack, and graph theory. There's so much just to do in advanced data structures, which is graph theory, which is smart building IoT data modeling. I have some ideas on vibe coding some of this really soon. But here's the theory lectures if you want a little bit of theory practice. Okay, so this is our vibe coded dashboard. So let's update this. I think this AWS IoT Core is pretty cool. I'm really impressed by this, and I can show you as well, but like I only notice a 30-second latency delay in the data to what I can see on the dashboard, which I think is really cool. 30 seconds, so that is like real time to me. Okay, so this is our Cloud Shell, and then like what I'm gonna do now is so I'm on here on my little server running locally. I think I've shown this a million times. It's this guy right here. That is my Ben server. So it's running right next to me, literally. And I'm remoted into it with Cursor. And Cursor's going to give me some commands to run to package everything and zip it and then upload it to AWS. And then AWS IoT Core, there's an acronym called SAM. That's like a serverless architecture model, I think it stands for. So it has all of the SAM configuration, and it appears to be working. It's all zipped, then you just upload it and run a few commands in here, and then it kind of takes off. Okay, so hopefully that makes sense. This is zipping up some packages, and then we'll upload this from the Windows computer right to AWS IoT Core, and it kind of configures everything. And then Ansible is just a tool I use to get little edge devices, Linux edge devices, kind of bootstrapped up and running. Okay. So here we are. This is Cursor, and it already has some steps for me to do. So this is all in the context too of Vibecode App 12. Let me zoom in a little bit. So this is already baked into the README of this as well, so people can follow the steps. So this first command is going to zip up in Linux world a tar.gz, which is a zip file. So then I can just, here's the file right here, what it produces in a tree, and I can just right click and download. And then this downloads to my Windows computer, replace my old one, and then I just have to go here now. First I have to remove the old one from AWS, paste, enter some Linux commands up there, and then now I upload the new zip file. There we go. So this is just uploading the SAM configuration, and then I'll do the full extraction, paste. SAM is now building it. I think this last command, SAM deploy force upload, this should be kind of setting everything up here. A couple different options. So Cursor's really good at kind of bootstrapping all of this, writing all of the Python code, and then we zip it all up here, and then it'll just launch in AWS side. Update in progress. So I want to go, okay, so it's done already. Then here's one of the Lambda functions is this URL right here, which I think I should be able to just refresh this instance. Okay, so it's loading data. Oh, look at that. Okay, so lots of data. Let's see if I can explain this here. So I did add some checkboxes here for which fault equations you want to see, and then also a checkbox to display the rolling average of the sensor data. So if you just see the temp sensor data, ooh, it looks like something dropped out here. That looks really odd. That looks like we should be throwing a fault. So this, you can see this data. This is 10 seconds data, probably a lot of data on AWS IoT Core. I've had this running for a couple days now. This is where I stuck it down by the AC vent in my office, so really cold air blasting out of the furnace registry. I have like so my little office that you can see behind me is just a really crappy residential split system in a teeny little office, so I have no control over the HVAC or anything like that. So this is just to demonstrate pretty much just a sensor, fault detection of a sensor for HVAC zone. But coming soon, we'll be doing a real HVAC system in Python. So this is AC vent, and then this is where I stuck it next to the exhaust vent on my little server behind me. So that runs about 100 degrees, 90, and then it's kind of going back and forth, playing around with it. So and if I zoom in here, then this is probably every time the furnace is running. So 66, so it can be kind of cold. Also this like little web interface, so this is a Lambda function of raw HTML file. So if you watch the other YouTubers on OpenClaw or Hermes, they're making all these crazy dashboards, and the AI is maintaining the HTML. They all say, "Thank God I'm not maintaining the HTML." Cursor has made this little dashboard for me, but I asked it to use Plotly, and it's a JavaScript library that makes really cool charts, and I love like the features for it. Like has lots of really cool zoom in, zoom out. You can just really zoom in if you want to, and you can even download a plot of what we have here. So in the future, once we get something useful, I love Plotly, and I think you could just dump this right into a report or something like that for a client. So that's where I'm going with it. Okay, so we have out of bounds faults. So if you look there, this is, I think the fault rule is set up for, to maintain these like these sensor bounds, which is 80 and 68, I think it is. So let's get into making the Python code to do this. I'm just going to zoom back out, and then yeah, there could be tons of false positives here. So like this is just an exercise to play around with a real sensor for one thing, and then play around with Python code to make faults. And then I also have another fault for a flatline sensor where there's just so much going on here, where guess what, this looks like lots of false positives. So let's see if we can fix this. And then there's also a rate per hour of another fault. Guess what, lots of false positives. So I have so many faults here that something is blatantly wrong with how we're calculating faults. So that's good. We just have to debug it now. The fun part of fault detection. Okay, so if I jump into this tab, I'm just calling it BACAPI, because we're kind of like baking this evaluate function into the back end of AWS, and then that's will I iterate over each time step in the database, and I would say update the database for true or false on every time step. So please reach out if you see any cool things to do, or if I'm missing something. I'm just doing a rule-based fault detection on every time step. And then I can do that either based off of rolling average data or actually the real raw reading. And this doing like really simple, like this is the bounds rule. If the degrees Fahrenheit reading is less than the bounds low or greater than the bounds high, guess what? That's a fault. Return true for that row of data. Then I'm also like baking into this too that the AWS Lambda function, it installs the datetime library. I'm not using that yet, but so we're kind of like almost working up to the way of being able to do pandas data frames, lots of date and time parsing, and then also the NumPy math library. I'm not using NumPy yet, just using math that's built into the Python programming language, but it's coming. So, and you also have the ability to go to different rules, which I'll demonstrate later, and add or create more variables. So, but I think like the first thing like we should do is kind of study a little bit offline. Sorry, this is, I need to get back to this. So I just wanted to demonstrate this a little bit. So this is like when it runs, you get an hour's worth of test data, which I think I have that. Okay, test window is 6 hours. Rolling average is computed at 10. And then down here, this will be a feature that you can upload to the large language model. So we could even chat with ChatGPT. And so if you would go and copy this, you could go, let's just start the conversation with ChatGPT. How does this look? Please eval. So basically, ChatGPT can we can start playing around with AI and helping us with our fault detection rule. Okay, so this is what I did. I'm going to get into VS Code just in Windows, on the Windows computer, just playing around with the raw data that I copied out of here. So what I did is I copied a whole bunch of this data, and if you can see right here, this is a dictionary with lots of different keys and values, degrees Fahrenheit, raw reading, timestamp, and a string of the that row of data. This is the timestamp in milliseconds, and then it's row and a row number. So what I want to do is just play around, kind of like a little bit of theory of like how we can play around with fault equations in Python, and then once we play around a little bit with being able to do this offline, then we can perhaps work with ChatGPT in doing this a little bit differently. Okay, so ChatGPT is already saying that we should do so we'll just kind of work with this a little bit, but we'll get back to using ChatGPT, and then probably on the sake of time is update the other fault rules, and then maybe we won't have a lot of false positives. Okay, so I am going to let me just get back here. So like we're on here viewing a web page that is served by AWS Lambda. And then like what it does when it basically, we play around with the Python code in the browser served from here, but it doesn't run in the browser. It's actually sending that Python code back to AWS, and then AWS Lambda SAM architecture runs, updates all the records in the database, which is the AWS Dynamo database. So what I'm doing here in VS Code in just a second, we're still here, but we're just playing around with data that's offline. Okay, so right now I'm just in AWS, and so this is data that I literally just copied it from the same window that I did with ChatGPT. So what it is, this is a list. It's a list of dictionaries. Just what I was saying before, row, timestamp, another timestamp that's a string. Maybe someday we'll get into using that with the date and time library in Python, or maybe even pandas. And then these are the sensor readings. These are real sensor readings, not made up. So like what I'm thinking about doing is just kind of manipulating this fake data, and then we can practice a little bit as well. Another thing that I want to do too is play around with evaluating batches of data. So like I want to make a function, I have that created already, that will grab the last 5 minutes of data, or even just 1 minute of data, and then we can calculate a high and low value based out of that limit. And then what I want to try and do on the live system is to, over the past hour, what is the rate of change that sensor saw, which I think it's 0.15 degrees Fahrenheit per hour. We could throw a fault. And the idea behind that is there's no, there could be a couple things, like there could be a mechanical issue. If it's real readings, could be something wrong mechanically with HVAC, or if it's there could be something wrong with electronics. So it's kind of meant to do both. So that's what I'm hoping to play around with. Okay, so what I want to do here is so this is just a plain, this is the evaluate function that gets sent to the backend in online. So this is just the offline version. So, and then what we're going to do here is just this was a list. Data was a list. And then like what this is going to do for row in data, I iterate across each row, and then pick a few things out of each row, each dictionary, and then pass it into the evaluate function, and let's take it from there. So okay, let's just try this out. So if we just do run this Python file, So what this did is I iterated across each row as expected, and we always return to false. So I think what I want to do is, so this is F string. So in our computer science theory, we covered strings and F strings and how you can inject data into an F string with curly brackets. And what I want to do is actually pull this out. So let's just say degree F, maybe do underscore, F equals this row of data. Then I could just pass this into the curly brackets. And then I want to do, let's see, this will be timestamp in milliseconds. Will be that row. So what we're doing is like we're grabbing these key and values out of the dictionary, and then we can assign it to variables within our function and then play around with it. Hopefully you guys can read this okay. Oh wait, shoot, this is wrong. I have to put this back into here because it's a row number. That was wrong. Then use this guy. Okay, I think that'll work. This is just a rounding feature to just round it to the 100th floating point value. And then I don't care about the config. What the config is, it's these things right here. It's just another dictionary of keys and values. And then what that is on the UI, it's just these things. So these, if you want to add in some kind of like a set point or some kind of a threshold or parameter to use, you set those up here in the browser, and then they come through as down here as another dictionary. But I think we might, for this, just kind of play around with without doing it. Okay, so let's play around with this. So like, if we wanted to hard code if the sensor is, let's just do a lower bounds. So the problem is with this real data, it hardly changes. If you see, it just changes by 1/10 of a degree, barely. So like what I might do is actually just change a couple rows of data. So here's 1, 2, 3. I'm just changing it from 69 to 66. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 rows of data. I modified from 69 to 66 just because, I mean, I could get really nitty gritty if I wanted to get into the 100th of a degree. Maybe I could, but for this, you know, just playing around with some algorithms, I think I'm just going to modify the data because it's just practice or fake data offline. And then I can do, so we covered this in computer science theory, like if, else, and operators for greater than or equal to. So I could do if degrees Fahrenheit is less than, oh yeah, we have to make some kind of like a threshold. We could just say, do like lower bounds. So this is just a value that won't change. I'll just say 68.0 as a float. Maybe we can do equals. Okay, so like if degrees Fahrenheit is less than or equal to lower bounds, then we could do something. We could say return true. And we could come up here and then we could actually shoot, there we go. We found it. Our fake data is 66. hey, we got a fault on that row of data. Okay, so the next thing that we could play around with is what I think the pros do is if there is, we need an n consecutive times that this expression is true for it to return a fault. I think you call it rolling window. It could be called anything, I guess. So let's just call it rolling window. Whoops, so this would be an integer, whole values. And then, so what I'm gonna call this in my world is, so this will be a hit, and if maybe I should put this to like 5. If we have greater than 5 hits, then hey, that's a fault. It's supposed to be to help try and tune out false positives if they exist. So that's how you can apply a rolling window. Okay, so I think I'm going to just put this here. So this number will change. I'm trying to think of like, so this number will change. I have to first define it as 0. And then I think I can pass it in to the function, call it hits equals hits. And then I have to pass it in here too. I'm just going to put it right in here, hits equals 0. Okay, so hits is defined outside of this. So this is basically where the program starts. Right here, hits is 0 for row and data. We'll pass in hits, and then we'll be putting hits back to 0 if we flag a fault, basically. Okay, so if we run across this, let me think about this for a second. We would want to hits plus equals 1. Debating about, now I have to return this value. Okay, I think we could do else. Okay, so we want to increment our hits on every time that we run across our thing, every time we evaluate true on our expression, and then we could say then here if hits is greater than or equal to our rolling window, then we return true. Else we just record this. Else we just return this. Okay, so I think this will work. Maybe we'll put in a print statement here just to record hits. See if we got any errors. So whenever we return two values in a Python function, it returns it as a tuple. Okay, I'm doing something wrong. Hits is not incrementing. I gotta think about this now. Okay, think. Trying not to cheat with AI, but it's going to come to that pretty soon. I wonder if we can return hits here. Okay, so this is incrementing now. Alright, so this is what we need to do, is return hits and pass it in again. Okay, so hits is incrementing. Okay, let's start out here. So here's a 69 value, 66. That's a hit. That's a second hit. And then by the time we get to the fourth to the fifth time we've had a hit, we need to go true, which we did. Okay, so like once we go true, we should we need to reset it. We need to reset it back down here. So we could say another if statement: if hits does not equal 0, hits equals 0. So basically what is happening when we get back to data going back from 66 to 69, we need to reset, put our hits back to 0. Okay, so let's run this. Okay, there we go. I think we have our hits reset. I can see it's back to 0. Okay, there we go. 66, okay, 69. That's when our expression went false, and then that's when we hit that. We reset our variable back to 0. Okay, fun. So this is computer science theory. So this is a little bit about how we could implement an upper bounds and a lower bounds computer science algorithm. And then I think it would need to, if this was a real world in HVAC, it would have to be applicable to the type of sensor. So if this was like a sensor on the chilled water system where the chiller is, doing lots of work, where all of a sudden the sensor could drop in 30 seconds, 5 degrees, it would have to be appropriate for the type. If the chiller's running, what should the range this should be reading, and then as with a zone temperature sensor. So I think like eventually we'll get into some more sophisticated faults where, for example, if the zone is unoccupied, what should be the range of temperatures we would expect to see? If the building is occupied, what is the range of values we should expect to see, and trying to think what else we could do. So it's kind of dependent on if a fan is running. We could even do a little bit. So that's a way to validate like mechanical aspects that they're functional. And then I think if we want to validate the electronics, that there's no flaky sensor readings, that we would want to just take a window of data, historical window of data, and then validate that there's no spikes, something weird happening, flaky sensor. So that is my idea, which I'm hoping to try for flatline sensor, and then also like a rate per degree per hour, rate of change, min and max value for a sensor, and then for 5 minutes. So let's try and get a little bit of that. Let's do one more push on this computer science theory, and then I think I'm going to go right to what I want to do is ask ChatGPT to write the code I'll be running on AWS, because it's better than I am at writing algorithms. But as long as we have some, computer science 101, not much going on here. Like, this is not complicated algorithms. Like, computer science algorithms can get so complicated I can't even understand it. Once you get into like dynamic programming and like you name it, it gets really, really hard. Okay, so like this is a function I made to grab the last 5 minutes of data, and let's try factoring this in, and then play around with another really basic algorithm for calculating the minimum and maximum values within 5 minutes, and then we can kind of conceptualize how that would look on the AWS data for maximum rate of change per I think an hour, and then per 15 minutes, where I think like that should flag if a sensor is flaky. I'm not really looking too much in that, and from a mechanical standpoint, like I feel like I would just evaluate if the sensor is maintaining some kind of bounds. I guess you could use it. You're just thinking a little bit more. Like if this is a heat exchanger, and like you turn the gas burner on, or you open that chilled water or hot water coil or a burner, the manufacturer would have a rate of change that they would expect to that air to warm up or that water to cool down. In theory, you could find snippets of data and kind of validate that the mechanical performance is still doing that. And then if that would be something to, there would be performance degradation fault equations. So that's like really complicated, but we'll get into that down the road. But now we're just kind of doing concept idea of like what this could look like. Okay, so I'm just going to get this into here. Okay, so I'm just going to plop another function in. I have to think how this would look. Okay, so what we would want to do is, now I can't remember how we look at this. So pass in rows and rows. Gosh, another thing we could just do right now is just use ChatGPT to do, maybe we'll just do that for sake of time. So I'm just going to ask AI is like, I want to look at the last 5 minutes of data and compute a rate of change. Let me think about this. let me just try something once. So we could do print row. Okay, so I guess row. I think we could actually print row number. So I'm going to try something once. Okay, so like we have a row here, row number, and what we could do is almost compare what would be the sensor values between this row and this row. Okay, so how would we do that? So we would want to trying to get some data here. Let's just do row, grab something else out of here. The degree F key. Okay, so for this row, what we want to do is grab, I iterate over rows and grab the previous row as we keep on iterating, and then feed those values into a function. So let's play around with that. So we could do this row temp equals this guy. Shoot. Sorry, guys. Paste that. And then, just debating on I'm debating about, oh, for sake of time, let's just okay, so let's just use ChatGPT. How could this function be enhanced to do last I'm just going to ask it how to use can you rewrite this to use the last 5 minutes data function, and then I want the evaluate function to calculate within that defined time period the degree F high and low values. Alright, let's just see what AI is saying. Kind of cheating a little bit here. It feels like cheating, but for sake of time, Okay, let's try this out. Try this one out too. It's also saying that we need a couple more config parameters. All right, let's test this out. Cheating a little bit here. All right, so no errors in the code. So this is basically looking back on 5 minutes of data Okay, so this is like creating another row, range, okay, so this is like one of our, this would have been a 5-minute range of data right here. We have a 66 and a 69, and then this is would be a range that it's seeing in that 5-minute window. Tolerance. All right, let's just look up what tolerance was. Oh, I know what this is for flatline sensor. Cool. I think you guys basically get the idea here. So if we set all of these values the same, there wouldn't be any differences between here. So like the fault is basically 0.05 of a degree if it's not changing within 5 minutes of data between here, that's a fault. Okay, so like, you know what I might just do is just jump right to the live system and let's just start pumping this stuff in. Can you make a, let's see, so a 15-minute version and an hour version for this, please. Okay, so we're just gonna go right to here and let's start just crunching some numbers. Someday we'll get into using NumPy. Okay, so what I want to do is get to flatline sensor. This is what it was doing before, which is kind of like a really weird way of getting data. Five minutes, hour. Let's just try this. Copy this hour function here. just going to be done with VS Code. Copy this guy. Degree F tolerance, we still have this. Sorry. So we still have. Alright, so then let's just test this. Here it is. So it's using the min and the max, which is built-in Python operators. Maybe someday we can use the NumPy library. All right, let's just test that. Test the rule. All right, so we have no errors. So like right now, this we did send this to the backend on AWS, and it's crunching these ranges for every time step. It's looking back on hours worth of data and crunching the max, high, and low values that it sees. Okay, so then let's try go live. So right now we're backfilling data on AWS. Knock on wood that there's no bugs. So what it does on the back end is it in 6-hour batches of data, it's updating the database. So basically 1,800 samples per chunk. That's 6 hours worth of data. It's just something I'm playing around with just to see if this works. All right, it says backfill done. Let's check it out. Wow, looks like we still have quite a few rate of change errors. I think there's something missing in this fault that it should be, if any, so basically for every time step we're looking backwards a whole hour's worth of data, and then if there's any anomaly in that entire hour, that whole hour should be a fault. So you know what I might just do is get back into here with ChatGPT. Let's just go, okay, wait. So I want to put this verbose prints. So let's test the rule again. So right now what this is just doing is testing just an hour's worth of data. And then this is what we can upload to the LLM. And then it even gives like the function so the LLM can read it. And then it can also look at the data too. Whoops. Copy that window. This is the data on the live FDD. I want, let's see, how to update the function where if this, let's see, how should we do this? Where if this fault occurs, it throws a fault on the entire look back window, which would be 1 hour. All rows would be in fault for that hour. Okay, let's just check this out. Our little vibe coding fault detection experiment. Hope you guys are liking this. This is kind of fun. all completely free so far. And completely DIY style, do it yourself. Okay, so we might have to do some more features. I don't think this will work. We might have to make some more updates to the backend to be able to do this. Well, maybe this is something we can then update for with cursor then. I think we'll have to make some updates in the backend of our little fault detection platform here to be able to add in this feature to be able to bulk update entire blocks as false, true or false. But maybe that's something that we can add in. I'm gonna have to add this. This might be a new feature. We just have to bake it in. Okay, so I'm gonna ask cursor, and this is how to add this into the platform where I want to have the ability to throw faults on an entire window of historical data. In this case, it is an hour of flatlined sensor reading. So I'm just going to paste that in by ChatGPT. Okay, so what else can I do? So I'm going to also give it this. This is what I gave ChatGPT, asking for it to do this, but I don't think the back end of the Lambda function can do this yet. Thoughts? Okay, so that's a big ask. There's a ton of data in that. Probably going to be a big cha-ching on the tokens. All right, so maybe this is just more things we have to add to this. So I've been wanting to add to this, I'll probably do this tomorrow, is the ability to plot multiple sensors, which is something when we get into more mechanical rules and everything like that, and the ability to work with a data model. So it's coming. So thanks for bearing with me today, kind of a little bit fumbly on the computer science side of things, but I think we'll just have to study things little by little and break it down into really small little chunks. Because I have seen it where the fault detection equations made by AI is just it doesn't make any sense to me how it's computing it. So I'll just kind of make it, dumb it down to really easy bite-sized chunks to understand, and then we can keep on playing around with this. So what is coming is we will get a live HVAC system. So I think I'm just going to start just vibe coding this, using AI as much as I can in the fault detection equations too, just for sake of time. I only have a little bit of time I can allocate to this most days. So the artificial intelligence, really expedites how fast you can do things. So, and then we can just dumb it down to bite-sized chunks, and yeah, let's take it from there. I will see you guys tomorrow, and I should have time. There's a weekend tomorrow, but I'll be usually carve out a little bit of time to kind of play around with my hobbies. So let's do it. I'll see you guys tomorrow. Hope you guys are liking this so far. Sorry if it's a little bit fumbly, but so I already see here that Cursor has made an update. So we'll probably have to add this. Ooh, what do we have here? Okay, yeah, so we do have to make an update to this. So I will just, yeah, like, so this will just be another thing to play around with. So, talk to you guys tomorrow.